Hello everyone, I am Abhijit Das from Indian Institute of Technology, Guwahati, India, and I welcome you all to the presentation of our paper titled Reducing Off-Chip Mispenalty by Exploiting Underutilized On-Chip Router Buffers. This is the outline of my presentation, so let's get started. The era of data-driven applications demand for quickest processing of information, and hence all the processing devices in and around us are realized by some form of a multi-core processor. To understand with an example, even the simplest of handheld devices like our mobile phones are powered with at least a quad-core or even an octa-core processor. These multi-core processors conceptually look like this, where they are arranged in a regular tiled fashion, and hence they are popularly known as tile chip multiprocessors or TCMPs. The TCMPs have processing elements or PEs which have a processor along with the on-chip caches. In most of the modern TCMPs, L2 cache serves as the last level cache or LLC. Processing elements communicate with one another through an underlying communication framework called network on chip or NOC. Everything travels as packets, and NOC has routers that facilitate the travel of packets from source to their destination. Let us try to understand the communication flow in a TCMP. For all the data and coherence related message exchange, an L1 cache controller communicates with the corresponding LLC or directory controller, which in turn communicates with the corresponding memory controller. Both of these communication are done through the underlying NOC. Our work is focused on the communication between an LLC directory controller and memory controller, and hence our discussion is limited to that. During a block replacement in LLC, evicted clean blocks are discarded whereas dirty blocks are sent for write back. We know that message in TCMPs travel as packets, and packets are further divided into flits. A request packet consists of a head flit, whereas a reply packet consists of a head flit followed by multiple body flits and ended by a tail flit. For example, a dirty block evicted from the LLC enter the local router and gets stored in one of the input buffers or VCs. It takes part in routing and arbitration decisions before going out of the router towards its destination. As shown in the figure, dirty block A evicted from the LLC is sent towards the memory controller for write back. However, due to temporal locality of reference, recently evicted LLC blocks are re-referenced within a small time interval. For example, the recently evicted block A is re-referenced and requested from the memory controller again. For standard multiprocessor applications, the average re-reference time is very less. However, the re-referenced block needs to be brought back from the off-chip memory, which is very expensive. It has also been observed that the LLC mispenalty is almost similar for all the applications. In another interesting observations, we found that router buffers are underutilized and at least one VC is always free except during peak network congestion. Now we have three observations, and if we carefully merge them, we can propose a solution to store evicted LLC blocks in underutilized VCs, and upon re-reference, we generate local replies from the routers to avoid off-chip mispenalty. In the proposed architecture, we have added an SRFD unit in NOC routers to facilitate our optimizations. We have modified packet header to include 4 additional flags, and we have also made minimal modification to the LLC directory controller and memory controller to maintain cache coherence with our optimizations. For local store, when an evicted LLC block reaches the local router, SRFD unit checks the store flag. If the store flag is found set, SRFD unit disables VC and switch arbitration to facilitate local store. It is as if we have logically cut the output path of a VC where the evicted block is stored. This way, we can keep the evicted block stored in the local router for as long as it is not interrupted. Some of the evicted clean LLC blocks are also sent to the routers for local store to improve our chances of local reply. To generate a local reply when a new LLC block request reaches the local router, SRFD unit checks the S flag to identify if it is a read request. If the flag is found set, SRFD compares the address of the requested block with all the stored LLC blocks. And if the address matches, appropriate steps are taken to send a local reply. The stored block is sent back to the same LLC block as a local reply, and the request is dropped as it need not travel any further. If the X flag is not set, meaning it is not a read request, then we check if it is a write request with the help of the X flag. If the X flag is set and the requested address has matched with a stored block, we perform similar steps for local reply but with an additional check of the dirty flag. If and only if the dirty flag is set for the matched stored block, we know that the block is exclusive and hence we can generate a local reply. However, if the matched block is not dirty, it is simply dropped as it need not be forwarded for write back. In this case, a local reply is not possible and hence the request is forwarded towards the memory controller. We cannot keep the evicted LLC blocks stored in the local router forever as it might create injection suppression during peak network congestion. So, when VCs are full, a locally stored dirty block is enabled for VC and switch arbitration to reach its destination for write back. Whereas for locally stored clean block, it is simply dropped as a write back is not necessary. We employed two approaches for forwarding and dropping locally stored LLC blocks called defensive and aggressive. When VCs are full, defensive approach dictates that if any one of the VCs have a stored block, it needs to be vacated. Whereas aggressive approach dictates that only when all the VCs have stored blocks, one of them is vacated. We have used an 8x8 NOC based TCMP and this is our system configuration. We have used GEM5 and decent simulators for performance and overhead analysis. We have considered 4 different architectures for evaluation where the baseline architecture is without any optimization and the other 3 architectures have different optimizations that we have proposed. All our results are normalized with respect to the baseline architecture. We have created diverse workload mixes and considered LLC miss penalty, network stall time, and system speedup for performance evaluation. As we can see, for all the workload mixes, our proposed architectures achieve significant performance gain. We also conducted a sensitivity analysis to understand the impact of design parameters, and these are the results. Additional SRFD unit works in parallel with the RC unit, hence it is not in the critical path of execution. 4 additional flags included in the packet header does not have any storage overhead, but the modified routers have a negligible area and leakage power overhead. However, improved performance reduces dynamic power consumption. To conclude, we learned that evicted LLC blocks are re-referenced within a small time interval and on-chip router buffers are underutilized. Hence, we proposed a set of NOC-based TCMP architectures to keep evicted LLC blocks stored in local router buffers and facilitate direct reply upon re-reference. Our future work includes looking for additional storage in and around NOC routers. That's all from my presentation. Due to the time constraint, I could not explain everything with sufficient details. However, if you are interested, you may read our paper and reach out to us for any discussion or clarification. Thank you for your attention.